So right now in calculus, we are working on solving applied maximum and minimum problems. Here's question number 25, found in the textbook. We want to figure out what the maximum surface area, or what the dimensions are, of a cylinder that will maximize the surface area of a sphere that's been inscribed in of a cylinder that's been inscribed in a sphere of radius r, capital R. So we're going to treat the radius of this sphere as a constant. We're going to call it capital R. And the goal is to find the dimensions of the cylinder that will maximize its surface area. So what we do first is we take a very thin slice through the center of the sphere and the cylinder, and we want to find a relationship between R and H, that is the height of the cylinder and the radius of the cylinder. We want to do this because at this stage in our study of calculus, we can't maximize or minimize a multivariable function. So we want to get our surface area in terms of one variable. So by looking at this picture here, I'm going to zoom in. Remember, the height of the cylinder is h, and the radius of the cylinder is r, so AC represents half the height, BC represents little r, and AB is also the radius of the sphere, so AB would be capital R. So using those values, I can use the Pythagorean Theorem and find a relationship between little r and h. So the height is equal to 2 times the square root of cap r squared minus little r squared. I substitute that into my surface area formula, and so the surface area of my cylinder can be expressed in terms of r. And so I get 2 pi r squared plus 4 pi r times the square root of cap r squared minus little r squared. Now we know at the end points, my natural domain here is from 0 to cap r, but if I plug 0 in for the radius, I get a surface area of 0. And if I plug in capital R for my surface area, then I have a major problem because I get 2 pi times cap r squared. The cylinder would come outside of the sphere, and that won't work either. So, okay, how do I do this? Well, I do this by finding ds dr and setting it equal to 0, and I solve for r. So I use my rules of differentiation. I'm going to have to use the product rule on part of that expression. So I end up with 4 pi r plus 4 pi times the square root of r squared cap r squared minus little r squared minus 4 pi little r squared all over the square root of cap r squared minus little r squared, all equal to 0. I have a 4 pi everywhere. The 4 pi contributes nothing to the solution, so I simply divide it out. And I'm left with r plus the square root of cap r squared minus little r squared over the square root of cap r squared minus little r squared equals 0. Now to solve this, I'm going to multiply both sides of the equation by the square root of cap r squared minus little r squared. And that gives me r times the square root of cap r squared minus little r squared plus cap r squared minus little r squared equals 0. Add little r squared, and subtract cap r squared to the other side, and I get little r square root of cap r squared minus little r squared equals 2 little r squared minus cap r squared. To solve this, I have to square both sides, and I get the following expression. Little r squared times cap r squared minus little r squared equals 4 little r's to the 4th minus 4 little r squared cap r squared plus cap r to the 4th. Distribute, set it equal to 0, and I end up with the following equation, which is not a quadratic, but it is quadratic in form. 5r to the 4th minus 5 cap r squared little r squared plus cap r to the 4th equals 0. So because it's quadratic in form, I can use the quadratic formula and set little r squared equal to 5 cap r squared plus or minus the square root of 25 cap r to the 4th minus 20 r to the cap r to the fourth all over 10. And then I simplify and reduce, take the square root of both sides. The negative solution doesn't work, so I'm ending up with little r is equal to capital R square root of 5 plus or minus the square root of 5 over 10. Substitute this back in to the height formula. Distribute and simplify. Now this is a negative cap r squared, and so when I distribute, the plus minus becomes a minus plus. That is important. That does matter. And so I end up with, finally, after simplification, the height is 2 cap r square root of 5 minus plus square root 5 over 10. Okay, so what are the dimensions that maximize the surface area? Well, it turns out that cap r times the square root of 5 plus the square root of 5 over 10, if I let that be my radius, then my height is 2r, 2 cap r, times the square root of 5 minus the square root of 5 over 10. These are the dimensions that maximize the surface area. Capital R is a constant, so if I let r equal 1, I could plug this in my calculator, and that's exactly how I got this graph. And so here's the maximum, which if I go down here, this would equal the square root of 5 plus the square root of 5 over 10. And so that's how I know to choose these ordered pairs and not the opposites or the conjugates. Also, if I plot dv/dr, I know that it's increasing and then still increasing, and then it's decreasing. So by the first derivative test, that makes this a local max. But it's the only local max, so that means it's an absolute max. And so now I've found the dimensions that maximize the surface area. God bless you, wherever you are today.